Okay, so in this lecture, we will discuss a little bit of parallel manipulators. In fact, because of the delay in covering the basic topics in this semester, once it seemed that finally the advanced topics may suffer a little, and parallel manipulators, it may not be possible at all to take up parallel manipulators. That was how it seemed. However, um, it would be very bad if you come to my class in this course and finally leave without anything on parallel manipulators, because parallel manipulators happen to be that field of research um, with which I started my research career, and quite a lot of my own original contributions are there in that field, which are sort of now among the basic subject matter of the field. So normally in this course, I devote some 3 to 4 lectures on this topic, but this time that much time is not there. So I will try to give you a snapshot by a quick, uh, tracing of one paper. Okay, so I will display that paper and cover the material in an order which is not exactly the order in which the paper is written, because that is for research presentation, that paper, the way it is drafted, where general statement comes first, examples come later. Okay. Uh, that way, it will be very difficult for you to understand the whole thing properly. What I will do, I will go up and down and cover the material in such an order that it comes to you in a sensible manner. Okay. So let me share the screen with you. Yes. So this paper, as it is, covers the dynamics of parallel manipulators in general. It's a general formulation. It's a general strategy for parallel manipulators of all kinds. Okay. So before this, actually, I actually worked on individual parallel manipulators, and from there, the pattern that I abstracted on my own work, this paper outlines the general reading from that pattern. So all parallel manipulators can be, or all, mostly, yes, parallel manipulators, all of them, and even some hybrid manipulators can be formulated for their dynamics through the strategy with which I actually worked on different manipulators first. So this happens to be the last paper that I communicated before coming to IIT Kanpur. Okay, so you see that this paper was received at the editorial desk in this at this time when I was still in IISc. I was yet to defend my thesis. Okay, and by the time, so that is why when it was sent from a different address. It was Department of Mechanical Engineering, IISc Bangalore. But for after acceptance, when we sent the final version, the addresses were changed. At that time, when it was sent first, both of us were in IISc. I was waiting for my PhD thesis report, and this gentleman was waiting for his master's thesis report, okay, MSc Engineering thesis report. So this was my formulation from top to bottom, and this fellow's master's thesis was actually on these examples. So this was our, in a way, dream paper together. which would be devoid of the processors. Okay. So, I mean, this is the only paper of mine which has been communicated with the cover letter, not on a faculty member's letterhead. Okay. Anyway, so it is a general strategy based on the Newton-Euler approach for the dynamic formulation of parallel manipulators. So I actually showed that Newton-Euler approach has some advantages over the Euler-Lagrange approach for dynamic formulation, particularly in case of parallel manipulators. Okay. The textbook tells you that for serial manipulators, Lagrange formulation has advantage. Even I have told that. And for serial manipulators, that is true. For parallel manipulators, Newton-Euler approach turns out to be better. For hybrid manipulators, they might compete very equally. Okay. So I should show you how parallel manipulators look and how they differ from serial manipulators. Okay. So I'll jump to page 16 to show you the picture of the most famous and most typical parallel manipulator. Mhm. This is going to be trouble. Yes. So this manipulator is called a Steward Platform. Okay. So this is the starting point of the study of parallel manipulators. And the original paper by Stewart was actually published in 1965. Okay. So here the end effector is called the platform. Okay. And for having 6 degrees of freedom, there is no long serial chain, rather the chain is parallel. Okay. So this is supported by 6 legs. Okay. When I say parallel, that means these legs are parallel, but not in the geometric sense, the circuit connection sense. The way you connect the platform to the base through alternative connections rather than through a single connection in series. So these are not parallel in geometric sense, but in the connection sense. Okay. Now the platform is connected to the base, fixed base, through 6 legs. Each leg is composed of one spherical joint at the end with the connecting with the platform, and a universal joint or a spherical joint connecting it with the base, and the leg itself is composed of 2 bodies, upper part and lower part, between which you have a prismatic actuation, sliding actuation. Okay. So you could have had a revolute connection also. Okay. So, and it is this which is actuated. So that means in every leg, one joint is actuated and the other joints are passive. Okay. So the 6 actuations which are in your control are connected in parallel. That is why it is called a parallel manipulator. And other parallel manipulators also share this trait with this. Now here, parallel manipulators differ from serial manipulators, and their properties, their applications are also different. So parallel manipulators typically are applied not for large sweeping motion, but for large forces to be supported, and motion is typically less, only in the spirit of adjustments. Okay, small adjustments within a little domain, and it is the accuracy and force carrying capacity for which parallel manipulators are really known. Okay. Now we go to the basics of how we work out its dynamics, inverse dynamics or dynamic equations, whatever you do. So the dynamic formulation strategy hinges around these two equations, which we saw even while discussing the dynamics of serial manipulators, right? So the total force on a body is equal to its mass into acceleration. And the total moment on the body and moment of the forces also about some point will be equal to this, that is the moment of the inertia force in a way, which has been taken on this side. Okay. So moment of the force giving this. Okay. So this sigma f is actually here. Okay. Plus moment of inertia of the body into alpha plus omega cross I omega, where again, so this is because of the 3D case. In the planar situation, this will be 0. Okay. So these two, Newton's equation and Euler's equation, will be applicable to each body. But on each body, we do not apply it completely in the dynamic formulation of this parallel manipulators. Okay. So we basically try to see its components along or about directions or axes where there is freedom. If our intention is to find only the dynamic equations and not bother about the constraint reactions. So parallel manipulators offer a good way to eliminate the passive joint reactions, okay, which do not do any work. So as you go about finding the dynamic equations, what you do first, rather than joint space analysis of parallel manipulators is facilitated if you conduct the analysis in the task space. Okay. So first you conduct the kinematic analysis of the end effector point or end effector body. Based on that, for each leg, you work out the position, velocity, and acceleration of the platform connection point. And that point onwards, the analysis of each leg gets decoupled. Okay. So you first decouple the legs, and now the legs will be fully analyzed. Okay. Now you study the kinematics and dynamics of the leg, and the leg may be composed of more than one bodies. Okay. So you consider the kinematics completely, and you take the dynamic equations and take the components of the vector dynamic equations along those directions in which there is freedom. So if there is a sliding prismatic freedom along some axis, then along some direction, then you take the force component in that direction. On the other hand, if there is a rotary freedom about some axis, you take the moment and consider its component along that direction or about that direction, that axis. And that gives you, and whether this particular joint, this particular axis or direction is actuated or not, doesn't matter. In either case, you do that. If it is actuated, then that actuator force or moment will come into picture. Otherwise, it will be just an equation which will relate other things. After you complete the analysis of kinematics and dynamics of the leg, you should get the force of the leg to the platform at the platform connection point in terms of the known and unknown quantities that are involved in the analysis. Now, from all such legs, you collect them and finally write the dynamic equations for the top or platform, the end effector. Okay. So this is basically the strategy. Now I'll take some examples after this, and in this dynamic analysis, you will come across two kinds of algebras: vector algebra and linear algebra, matrix. Okay. Now, when you manipulate the standard expressions algebraically, then um, there are some small steps in which some vector algebra kind of expressions need to be put in matrix algebra notation. And for that, a lot of algebraic manipulation is involved. For that, we have two rules. Okay. For example, suppose x is the coordinate or variable of the problem, and so x double dot is an acceleration component, okay, which is to be treated as an unknown variable kind of thing. On the other hand, a is something like a constant, b is another thing which is like a constant. These are also vectors. Okay, so a dot x double dot becomes a scalar. Okay, scalar but variable because x double dot is involved. So this is scalar into this vector. Okay. And when you try to put things in the matrix vector notation, you typically need the unknown things to be put on the rightmost end. Okay. So something into x double dot. But here you see x double dot is tucked inside in this scalar with dot product with this vector a, and on this side we have a vector. So to handle that, you first say that b is the scalar, this fellow is the vector. Whether we write the vector on this side or vector on this side, it doesn't matter. So write the vector on this side. Then say that a dot something is basically the inner product in the case of vector algebra is nothing but a transpose that something. So write that a transpose that something. Then you say this is a column vector, a transpose is a row vector, this is another column vector. Now all of them are matrices. So matrix multiplication is associative. So rather than multiplying a and a transpose and x double dot before, we multiply these two first. So then we get b a transpose x double dot. Now b a transpose is a matrix and this fellow is a vector which has come on the right side. So this is the first rule. And this will apply irrespective of whether your space is 2D or 3D. Now, this was the handling of the dot product. Now we will handle the cross product. When you have a cross x double dot and you want to put it in the matrix sense, then what happens? First, let us see for a planar system. In the planar system, this will mean a1 x2 double dot minus a2 x1 double dot, like this. So now collect the coefficients a on this side and put the variables on this side. So coefficient of x1 double dot is minus a2, that is this, and coefficient of x2 double dot is a1, which is this. Okay. So you can say that from the vector a1, a2, how do you get this vector? First, you interchange the coordinates. A1 comes here, a2 goes there. Then the sign of the first one is reversed, and then you take the transpose. So the first two things, flip the two coordinates and make it negative. Make the first one negative. That is represented here by a subscript perpendicular sign. That means whatever is the vector a, if you turn it by a right angle anti-clockwise, okay, then you get this vector a perpendicular. Because if this vector is a1, a2, then by turning it to the anti-clockwise direction by 90 degree, you get minus a2, a1, okay, and then take transpose. This is what you get in 2D. Okay. In 3D, what you need to do is similar cross product. When you evaluate in 3D, then you can see that this cross product turns out to be equivalent to a matrix A tilde into vector X double dot, where A tilde is this skew symmetric matrix. You see, this is a similar thing that we saw in the description in the development of the angular velocity tensor. Okay, I mean angular velocity vector from the rotation tensor and its rate. It is a similar skew symmetric matrix. Okay. So whenever the cross product we have to put in the form of matrix expressions, in place of A cross something, we will put this matrix A tilde, this skew symmetric matrix A tilde into that something. Okay. Now, with these 2-3 rules in the background, we go to the, okay, this we have already discussed. The final point is kinematics and dynamics of the platform, from which we get the dynamic equations in this form, in which this mx is the total inertia matrix, which has a component from the platform and a component from each leg. Similarly, this is the vector of centripetal and chorially components, okay? And that also will have similar parts. This is the mapped output of the actuator torques or actuator forces to the platform coordinate frame. Make note that these generalized coordinates are platform coordinates, not the joint coordinates. That is why you have to map the input forces towards output rather than output forces to the input. In that case, in the serial manipulator case, we actually found J transpose external force coming on the actuator torque side, right? Here it is H times tau going to the platform side, the end effector side, because the formulation is in task space, and the external force and moment remain just like that, because that is the coordinate frame in which the analysis is being made. Okay. So this Hx we refer to as the force transformation matrix. Okay. And in sense, it is equivalent to the Jacobian transpose, because the velocity also gets basically mapped from output to input rather than this way by the matrix, by the corresponding matrix J, which is actually H transpose. Okay. So this finally gives you the dynamic equations. And let us see through examples how we get hold of that. This right now we bypass. First we go to the examples. Okay. First we talk about planar manipulators. Okay. To keep things simple. 5-bar with prismatic actuations. See the picture first. Yes. At this point, I'll take just a little half-minute break and rejoin you. Okay. So this is basically a 5-bar mechanism with prismatic actuations. Okay. So one link is the base, then each leg is composed of 2 links, and one revolute joint here, one prismatic joint here, and finally one revolute joint. And this point is the end effector. This point is the location of the end effector. And that location, xy, is actually the basic coordinates of analysis here. And that vector xy in this frame, this vector from the origin of this frame to P, OP, is the translation T. Okay. This has x and y. And This is a base point B1 fixed in this frame, and this is other base point B2. Now, from the leg analysis, I remove the subscript for convenience to write less basically. Okay. So for each leg, this top point T minus this base point B is this. This is a leg vector, and the leg length is its magnitude, and the unit vector along the direction of leg is this, right? Now we can differentiate any of these. We can differentiate this and then get L dot, and from here, I mean, we can get, if we want, S dot also, but normally we don't want that most of the time. Okay, what we want is the velocity component along the leg. So basically, rather than differentiating and then evaluating things, we directly talk in terms of the derivative of this vector T dot. So the velocity of the end vector point P, its direction, its component along the S vector along the leg is this. Okay, and that velocity, you can take its perpendicular component that is perpendicular to the leg, and that perpendicular component of the velocity is actually omega cross L. So omega has been shown with W. Okay, because actual symbol omega we reserve for the angular velocity of the platform when platform is not a point, because this is just an example. Okay, so in other examples, the platform can be a body. Okay. So we talk about the angular velocity of the leg by this W. So this is basically W1, W2. Okay. So that is the angular velocity into L will be the velocity of the platform point or end effector point in the direction perpendicular to the leg. Similarly, the acceleration of the point P is T double dot, and it's the L double dot we can get by taking its component along the leg and add this omega square L. Okay, because what happens is the acceleration of the point in that axial direction actually is L double dot minus omega square L. So that minus omega square L, if we bring the omega square L on this side, then we actually evaluate L double dot in terms of these. See, everything we are trying to evaluate in terms of T, T dot, and T double dot. Okay. And on this side, we have got L, L dot, L double dot in terms of T, T double dot, T, T dot, T double dot. Because in terms of T, we are basically going to develop the equations. They are the generalized coordinates. Now, kinematics is complete. Now we go to, okay, angular acceleration of the leg also we will need. So alpha cross L plus twice omega cross L dot into the unit vector along that direction is the other component, the tangential component of the acceleration. So the tangential component we first take acceleration's tangential component. From that we subtract the Coriolis magnitude, and then that becomes alpha into L. So we divide by alpha, and we divide by L and get the angular acceleration. The way the angular velocity of the leg we are showing by W, the angular acceleration of the leg we are showing by capital A. Now, wherever is the position of the lower part of the leg RD, Okay, it could have been written as RL, but somehow we used up and down rather than upper and lower. Okay, so RD is the location of the center of mass of the lower part of the link, lower part of the link. So its acceleration we get like this, and similarly the upper part, for that the acceleration of the CG we get like this, and in that notice that L double dot will come into picture because the intermediate sliding acceleration of the joint will come into picture. Okay, and then we consider the force at the top point, connection point, and that force has two components. One is along the leg, that is why it has dot product with S. Okay, gravity component it has come, inertia component has come, and the actuator force has come. So what we are doing is basically we are talking about the equilibrium of the upper part of the leg only, and that is why this force is coming. Okay, only upper part. You see, inertia of only upper part is coming. Mass of only upper part is coming. We are considering the equilibrium of the upper part of the leg, not equilibrium, basically dynamics. Okay, and taking its component along the leg. So we get the force given by this leg to the platform along the leg. Okay, this expression. And now the other component we throw away. We don't need it because that will give a unnecessary, too many unknowns it will involve and we will not have anything. Okay, so then we consider the complete leg together. That will involve upper part of the leg, lower part of the leg. Okay, this, and the moment of inertia of both the parts into angular acceleration. This will be the force component at the platform coordinate. Now this complete equilibrium, now this complete force equation, moment equation actually, this complete moment equation of the entire leg, for that we basically consider the moment about the base connection point. So that means the forces coming from the base connection point get eliminated completely. And that is L times Fp, where Fp is the force from this leg on the platform in the direction perpendicular to the leg. Okay, so along the leg we got here, perpendicular to the leg we get from here. Okay, so the resultant reaction force is this into S, small s, and Fp into the perpendicular unit vector. Okay, so this becomes the contribution of this leg to the end effector. Fine. Now, all these long and complicated expressions we put inside this FA and this FP, all these complicated expressions we put inside this, simplify through those rules, and that simplification results in this equation. Okay, where the actuator force gets involved here, acceleration of the end effector point gets into here, and this Q is some sort of partial contribution in the inertia matrix, which is this. I mean, that insertion and manipulation will give you this. And U is the bunch of centripetal, Coriolis, and gravity terms. Okay? If friction terms U included, then that also would come there. Now, this analysis is complete for the leg part. Now, each of these legs will go through this analysis, and for each of these legs, the F that you would get would be actually F1, F2. Okay. Now, F1 plus F2 plus external force together is 0, because this is a point, you see. Okay. So for which there is no separate mass, no separate moment of inertia, and so on. So that's it. So from here we get the equation in this form, where the coefficient of t double dot, see t double dot and f come from there, right? So whatever was the coefficient of the small f there, the actuator force, that now comes with S1 and S2 here. Okay, because one came with F1 S1, the other came with F2 S2. So this becomes a force transformation matrix sitting here. This is external force coming from here, and these two will come from the sum of whatever we got from there. So this kind of analysis can be conducted for the 5-bar with revolute actuations also. Almost the whole thing conceptually the same way, but actually equations will differ. So first you will have the leg in this form rather than this. Okay. So this is the leg vector. Okay. And you can have these things as it is, but then you will need to break down into the angles. Okay. And then you consider the unit vectors along the lower link and the upper link. So this unit vector will be C, this unit vector will be D. To be precise, C1, D1, and here it will be C2, D2. Okay. And these angles will define their orientation. So like this so C is this, and according to that D you can find. So basically theta is the angle which will be in your hand. This is what you basically, this from here to here, this angle theta is what you will actuate. Okay. So angular velocities of the lower and upper links you can find out by 2R manipulator kind of analysis, which we know. Okay, this we have done earlier. So this is actually the serial bit. Okay. And then when you carry out the now similarly acceleration analysis like 2R manipulator, you find out the acceleration of the CG of the lower part, acceleration of the CG of the upper part, okay, in terms of the acceleration of the top connection point. And this term here is the velocity dependent term. You see that. Okay. Now, when you consider the dynamics of the leg, you again first consider the upper part only, and for that you take one component of the force. No, for the upper part you consider only moment, because from the upper part you get the perpendicular component. First consider the moment equation of the upper part of the upper link about the point J, so that those forces get eliminated, and that thereby you will get the perpendicular component of the force. Okay, this, and then you consider the whole thing again moment equilibrium, both times moment equilibrium, because now in the leg both the joints are revolute. So both times you take moment equilibrium. Okay. So now complete leg moment equilibrium. Okay. About the base point, and from that you get in another direction. Now these two are not perpendicular. These you cannot directly add up. So you have to work out what is the correct f. So basically that is why we did not add up the two components from there. We got one equation for f from here and another equation for f from here. And now you solve these two to get f. Okay. So after you got that with very complicated expressions, you go to the platform and add up everything. Platform is a single point here. Okay. So like this, you can carry out the analysis for 3 degree of freedom planar manipulator also. So like this. Okay. 3 degree of freedom planar manipulator with 3 links. In terms of the mechanism theory, this is actually an 8-link mechanism. One link is the base, one link is the platform, and 2 links here, 2 links here, 2 links here. Okay. And this is 3 degrees of freedom. And now, if you have a fourth leg like this, that doesn't make it 4 degrees of freedom, because the degree of freedom is still 3. Because here, in the case of parallel manipulators, the degrees of freedom don't add. Okay. Basically, degrees of constraints add. Okay. And therefore, degrees of freedom are like common freedom allowed by each leg. So this leg allows 3 degrees of freedom, this leg allows 3 degrees of freedom, and this leg allows 3 degrees of freedom. The fourth leg, if joined, will also allow 3 degrees of freedom only, and therefore this guy will have 3 degrees of freedom. Okay. Now this is a case of force redundancy, which I was talking about in the previous lecture. Now, rather than supporting the platform with 3 forces, you have the luxury of supporting it with the help of 4 forces. And therefore, you will, in order to solve for these actuator forces, you will typically have a system of 3 equations only in 4 unknowns. And therefore, infinite combinations of F1, F2, F3, F4 you can have to successfully support it. And therefore, you can choose. That is the redundancy there. Okay. So in any case, the dynamic formulation will have the same procedure, except that in this case, in the non-redundant case, you have to handle 3 legs on the way. Here you have to include 4 legs. So in the loop, whether you put 3 or 4, so for the fourth one also you have to give data, and then that analysis will take place. The process is same. Okay, so we'll not go into the details of it, except one remark that when considering the dynamics of the platform, finally, whether in this case or whether in this case, we will not only take the force equation of this platform, total force equal to mass into acceleration of this, not only that, but moment also, moment equation also. And another thing is that since the position of this origin is the generalized coordinates now, x, y, theta of this, okay, therefore, the leg, for getting the leg equation, first we have to get the position of this, and that is easy. Rotation matrix multiplied by this common, this constant vector as expressed in this platform frame, plus this translation vector. Okay, the translation vector plus this constant vector as expressed in platform frame pre-multiplied with the rotation matrix corresponding to angle theta, that will give you this point here in this frame. Okay, like this also. Okay, like that, this also, this also. So and then onwards it will be similar. So this detailed analysis we omit, rather we utilize the time to go for some special cases. The Steward platform is not very complicated, but big system. Okay. So of course it is special, so that complication will come here. So in terms of the position of this point in the base frame and its orientation, you can work out each point like the vector t plus RP. Okay. So T plus RPI minus VI. So that will give you this leg vector. And then you consider its kinematics first. Okay. That is, based on the leg vector, you can get the leg length and therefore the unit vector along the leg. So the entire process is same except that it will now take place in 3D. And then you will talk about its force contribution. Okay, so from this base, if you take this, then this is the base point that you will come in, that you will have to talk about, not this, because this base point is related to this platform point. Okay, so fine. So then you will talk about its velocity. Okay, the component of the velocity along this direction will be L dot, and in the perpendicular direction, that will actually give you the angular velocity of this. Okay, omega cross this vector. Similarly, acceleration you can get. Fourier component will enter into picture there. And then when you consider dynamics, for the upper part, you will consider force equilibrium only in this direction. Okay, and that way you will involve the actuator force. Then for the complete leg, you will consider its moment equation about the axis about which it has, I mean, about this axis, this from through this point, from this point, and from this point when you consider, you will get actually a 3D vector of which you have to take the correct component. The component along this direction you have to throw away because that is zero actually. Okay, because the force is a force in this direction will not produce a moment along that. Okay, so anyway, so this Steward platform case we omit because that is also not there in this. On this, actually, I had my earlier publications which gave the full details of that. But similar thing you will get in this case. This example is actually that of a hybrid manipulator, where all the actuations are not in parallel, but there are 3 legs rather than 6, and each leg has 2 inputs. Okay, so that is why it is hybrid. So one leg has 2 inputs, 2 actuations, another leg has another pair of actuations, and third leg has another pair of actuations. So these 3 individually are serial manipulators, but under actuated. Okay, and now these 3 join in parallel. So it's a hybrid manipulator. So a hybrid manipulator is typically a manipulator in which either serial components are in parallel or parallel components are in series. Okay. So if you had parallel system of 2, then another parallel system of 2 over that on the roof of it, and then another 2 at the top floor, then it would be another kind of hybrid manipulator. Okay. So this 3 PRPS, prismatic, revolute, prismatic, spherical, like this. So in this prismatic joint is actuated, this prismatic joint is actuated, this revolute joint is not actuated. Okay? So here again, you work out the leg vector first. So the leg vector will be from the base frame to the platform frame, this vector t plus this vector. Okay, locally it will be available as pi. Now you have to transform it to rpi, r showing the orientation of the platform with respect to the base. So t plus rpi, okay, which is q. So q is rp. Okay, so t plus q minus this base point wherever it's fixed, wherever it is fixed. Okay, and minus dk. Now d is actually this actuation. Okay, and K is a unit vector. So that takes you at this point. Okay. And this is in a way the leg. And this is the position of the bottom connection of the leg, which is also variable. Okay. So this is how you work out the leg vector. No, basically, you are taking it. So D is T plus Q minus B dot K. So T plus Q brings you here, then minus B. Okay, so from that you subtract this. Okay, and of that you take this component. Okay, so this is what takes you from. So dk is this vector. So basically the complete leg, from the complete leg you remove this, and so this vector you get. Okay. So anyway, so you get this, and then based on the leg length, based on the length of this, you get L and the unit vector along this, and so on. And the similar analysis, step by step, you carry out over the leg. And when you consider the dynamics, basically, let us go to the dynamics part. Acceleration analysis will go on like that. And here, L double dot and D double dot, both are the joint accelerations, because there are two prismatic freedoms in the leg. So that is why L double dot and D double dot both are evaluated in terms of the platform acceleration, AP. Okay. Now, three parts of the leg: the lower part, the middle part, and upper part, for which you work out the acceleration expressions. Okay. In terms of the D double dot, L double dot, and velocity related terms, velocity dependent terms. Okay. Now, you consider the force equation of the upper part of the leg in the leg direction. So you get along the leg. Okay. And then you consider two of the entire leg. The leg plus this, the whole thing. The whole thing you consider together. And for that, you take the component along the first prismatic actuation, okay, along the k axis, and then you get another equation. So these two are two perpendicular components of the force that this leg will give at the top. Okay, so if the platform connection point force along the leg and along the k axis, okay, and in between joint is revolute. Okay, in between joint is revolute. So where from here the two links are included. So consider the upper and middle part together, and since this joint is revolute, don't take its force equation, take its moment equation, and the component of the moment equation along or about, basically about this axis, about the axis k. That will give you the expression for the third perpendicular component of the force. That is this equation. So the LFP is the third perpendicular component. Okay. So you see R plus F is this. Now you put the total force together, force along the S, force along K, and force perpendicular to both. Okay, that is a normal direction. So when you take the unit vectors and the magnitudes together and get this is the force from the leg to the at the platform connection point. Okay, and now getting all those expressions from there and putting things inside. As you simplify, you get that force vector in this form. AP is the acceleration of the platform point, for which the coefficient is a matrix, which is a symmetric matrix, because it will actually form a component in the inertia matrix. Then this U, which has the centripetal, Coriolis, and the gravity terms. These are the two corresponding actuation forces mapped by K and S as expected. K and S are unit vectors. Okay. Now this expression is too big. And then finally you consider the force and moment of the platform and get the final 6 equations. And now in the paper, as you read through, you will find that many times I am talking about considering equilibrium equations rather than dynamic equations. The reason is that the sense in which these equations are written are actually Newton-Euler, but in the equivalent D'Alembert sense, where you take the inertia force on this side and consider that also a force, and then you pretend as if you are writing equilibrium equations. So that is why we are talking about equilibrium rather than dynamics motion, though acceleration terms are there. Okay, so inertia forces and inertia moments are actually put on the other side, and in the D'Alembert sense, the equations are developed, which is equivalent. Okay, so in this form, you get the final dynamic equations in which the acceleration vector is this: 2 linear accelerations, 3 linear accelerations, and 3 angular accelerations. This will have the other terms in the dynamic equations: centripetal, Coriolis, and gravity terms. This is the mapped actuator forces. These are the external force and moment. E3 is 3 by 3 identity matrix. Okay, you see the 3 k vectors and 3 s vectors will appear to map the forces, and their cross products like this will appear to map the moments. I mean, map the forces to the moments. And these are the 6 actuation forces along K1, K2, K3, along S1, S2, S3, because these are the prismatic directions, force directions. A similar thing could be 3 RRRS, where it would be revolute joint, revolute joint, revolute joint, finally spherical joint. Basically, the two prismatic actuations could be replaced with revolute actuations. In that case, for each step, we will consider only moment equations. Okay, so moment equation of only this about this axis, moment equation of these two together about this axis, and moment equation of the entire 3-link assembly about this axis. And that is how we can construct the scalar equations which we need. From there, we will get the components, scalar components of 3 vectors, three scalar components of the force magnitude here, but they will be in general oblique. But from 3 equations, we can solve for the force vector. And those force vectors will be assembled when we consider the platform dynamics, okay? Platform moment, force and moment equations. And you will get the equations. We will not go into the details of that. This is another case, 3 RPS parallel manipulator. And this is a problem. This has a problem. This has a problem because it is like in the 3 PRPS case, the first prismatic joint has been locked. Okay. So the first prismatic joint of 3 PRPS case, if you lock in each leg, then what you get is this. Okay. So this will actually not have 6 degrees of freedom. This will actually have only 3 degrees of freedom. Okay. But the equations will have to include forces and moments, everything, and it will get a huge 6 equations. And the shortfall of the number of degrees of freedom with the number of equations that are handling that actually gives you some constraint equations. So so you have Lagrange multipliers along those directions now. Okay, and these will be constraint forces. Okay, so now these three equations will operate as constraints. So the final equation will appear like this only. Basically, you have locked three joints of the earlier case that we discussed. Okay, so the equations are more or less similar, except that k component of the force will be missing. Okay, acceleration will also not have that component because that is constrained by this. Okay, so the result will be a system of differential algebraic equations. So this is the differential equation, 6 of them. Okay, 6 of the differential equations and 3 constraint equations like this. Okay. Now, at the end, I will advise you. I mean, we will not go through that because that is actually a little qualitative assessment of what are the things that is happening. There is a kind of situations that we have considered. Okay. Yes. From that, you will see that there are some ordinary non-redundant parallel manipulators. Then there are hybrid manipulators. Then there can be manipulators with static redundancy, which we saw one example in the planar 3 degree of freedom case. And there can be manipulators with actuation redundancy also, because in a leg in which we had 3 joints but only 2 of them were actuated, we could have put actuations at all 3 of them. Okay, but only 2 of them would be really needed. So that would be a case of actuation redundancy. And at the time of control, you could actually decide which 2 we actuate, or if we actuate all 3, then in what distribution. So for all of these, the dynamic equations will appear in the same form in the standard style. Okay, in the same steps as we have outlined. There are some special cases. Some of them have come, which I call as non-redundant case. Now, one possibility is having a kinematic redundancy. That is where a three-link leg we have considered, okay, with three joint. If we had a four joint chain for that leg, that would involve a kinematic redundancy, and that for that you would put another extra actuator. Now, in that case, the dynamic equations formulated completely in the joint space would not be enough. Okay. Apart from the XYZ alpha beta gamma of the platform, you will need to consider that extra joint variable also shown as theta here as an extra degree of freedom, which has to be brought in. Okay. And therefore, the dynamic equations will appear in this extended form, where, right, unlike earlier, this mxx will not complete the inertia matrix. It will be like this big. Okay. So if in each leg you have one such extra kinematic redundancy, then they will together form a vector here. Okay, the dynamic equations will be large, degrees of freedom will be large. Okay, but with this additional dimensions brought in, you can formulate the dynamic equations. Then, if you have got that kind of an extra joint, but you do not actuate that, then you get a case of manipulators with passive freedom. Okay? And That you can get as a special case of this, because there what you do, basically that corresponding actuator is missing, right? The corresponding actuation is missing. Okay. So to throw the part coming for that, you can put this tau here, and below you put 0, because that actuation is missing. Okay. So this will give you the dynamic equations for the manipulators with passive freedom. But the inertia, etc., will come. So those things are included here as it is. So in order to show that this is actuated and this is passive, here I have included put theta, here I have included phi. Okay. And the other case, manipulators with inadequate actuations, we actually handled one such case in the 3 RPS manipulator. Okay. And there the final system appears as a system of differential algebraic equations, in which differential equations are too many, and then the surplus is accounted for by the constraint equations. Okay. So this single paper we keep as the material for this semester's discussion on parallel manipulators, and so I will upload this along with the subject matter with the lecture. Okay, thank you.